We use a scan code to send the message to the I/O port. Keyboards have fewer than 128 keys, so these codes are designated in 7 bits, and the 8th bit is used to show the interrupts. The interrupts start when you press down a key, and then again when you let off the key. Echoing is what shows what you're typing, and it shows it on the screen. There are 2 types of modes that keyboards use. You have conical mode, which is described as line-oriented mode, and non-conical mode, which is described as character-oriented mode. When operating in conical mode, you use special input characters to do and edit what you're working in. For mice, there are 2 types of mice. One is a trackball mice, the one that has the rubber ball on the bottom is the trackball. And there's the optical mice, which is equipped with one or more many diodes and photodetectors at the bottom. Minimum distance that a mice moves is about 1 millimeter. This is called a Mickey. The message that it sends back and forth contains delta X, delta Y, and how many buttons it has. These messages are usually sent up to 40 times a second. Mice can only calculate the change in position and not the absolute position. Alright, monitors. These use text windows. These are programs that sends characters to current window and they're displayed there. Usually a block of characters, for example, a line is written, is used in one system call. Escape sequences. Most output drivers support a series of commands. These are called escape sequences. When you're using a screen editor or other programs, you need to update what's on the screen by replacing it. This is what you use, escape sequences. The xlib is just a library of procedures for accessing the X functionality on the X Windows system. X Windows system is just a Windows system. It's not a complete GUI. You need other layers on top of it to present a full GUI. The X Windows management Windows management is not part of X itself, but it's a separate program run as like a Windows manager. It sends commands to the X server telling it what to do. Often these are on the same machine, but they don't necessarily have to be. And the TCP and IP connection X, there are 4 types of messages that are sent over the connection. One is drawing commands from the program to the workstation. Number 2, replies by the workstation, the program queries, keyboard, mouse, and other event announcements and error messages.
So regarding UI and thin clients, the big idea here, or one of the big ideas that prefaces the whole concept, is decentralized versus centralized computing. Initially with things like ENIAC and all that, that was considered a personal computer back in the day. Then we hit the timeshare era, which is where we have this concept of a centralized one big server and then multiple people access it sort of deal. And then we eventually hit the PC era, going back to the decentralized concept, where everyone has their own independent system that they run with whatever type of software they have. The problem that arises with PC computing that most people tend to overlook is the maintenance aspect of everything. People don't really want to maintain their computers. You normally don't see people as a whole backing up their data constantly and consistently. And this leads to people complaining whenever inevitably power surge happens, their computer gets fried, and they're like, where's all my data? And that's just something to be mindful of as you move forward in choosing whether you want decentralized or centralized systems being your primary computing source. Now, thin clients sort of evolved from the X Windows system, and the goal is to have high performance computing with essentially no administration of your computing device. And The staple example of this in modern times is the Chromebook, because you run essentially everything through web apps, because the Chromebook is intended to be always online. And that is where we're going. There have been other systems in modern times that sort of revolve around the same concept, but web clients are the primary thing that we're moving toward, as opposed to just straight from your PC. You can see this with things like email. That's currently almost exclusively done in browser now for standard users. So that covers thin clients.
I'm going to talk about power management. There are two general approaches for reducing energy consumption. One is for the operating system to turn off the parts. That's mostly for I/O devices. When they're not in use because the device is off, uses little or no energy. The second one is for the application program to use less energy. That may slow the quality of the user experience, but it will stretch out the battery time. Most of the vendors conserve battery by designing the CPU and memory in I/O devices to have multiple states. We're all pretty familiar with on, off, hibernating, sleeping. You set your computer to sleep if you're just going to have it off for a bit. We can talk about power management more and operating system issues, because operating system plays a key role in energy management. Controls all the devices, so it must know what device to shut down and when to shut it down. As far as the display, many operating systems attempt to save energy by shutting down the display when there's been no activity for some time. Changing how the brightness on the screen is an effect on when the battery is charged. For the hard disk takes substantial energy to keep it spinning, even if it isn't being used. So like he's talking about with thin clients and notebooks, they'll spin down the disk after a certain number of idle minutes. With the CPU, whenever the CPU is idle, it goes to sleep. On many computers, there's a relationship between the CPU voltage, clock cycle, and power usage. The CPU voltage can be reduced in the software, it saves energy, but also reduces the clock cycle. That can make it slower. There's two options for saving energy with the memory. The cache can be flushed or switched off, which is where it'll enter a sleep state. Or then you can always reload the memory from main memory. A more drastic option is to write the contents of the main memory to the disk and then switch off the main memory itself. But then you have the computer in hibernation. For wireless communication, messages have to buffer or wait when being sent or received because the radio transmitter and receiver aren't always powered on. For thermal management, operating systems have to manage temperature of the CPU because they can get really hot due to their high speeds. Some of the systems don't have fans, so they may have to turn down the backlight or slow the CPU or even the disk. For battery management, mobile devices now use smart batteries, and those can communicate with the operating system. These can be instructed to change various operational parameters to maintain the power. And then for the driver interface, there's the advanced configuration and power interface. So let's say you're not using your mouse for a long time, you touch it again, it'll tell the computer to turn it back on.
You guys gonna ask?
So now
Are
we're
you
going to talk about clocks.
you gonna
We're
ask
going to
anything?
focus on the hardware
Give you
portion.
candy?
Clocks in general help maintain the time of day and prevent a process from monopolizing the CPU, among other features. Three components of clock is the crystal oscillator, counter, and the holding register. So what happens is a piece of quartz crystal is when it's properly cut and mounted under tension, it can be made to generate a periodic signal of very great accuracy. And using electronics, the signal is synchronized to the computer's circuits. And then the signal is fed into the counter to make it count down to 0. And when it gets to 0, it causes a CPU interrupt. So there's two different programmable modes. One-shot mode is when the clock is started, it copies the holding register into the counter, and then decrements the counter at each pulse from the crystal. When the counter hits a 0, it causes an interrupt and stops until it is started again by the software. Then you have square wave mode. After getting to 0 and causing the interrupt, the holding register is automatically copied into the counter, and the process indefinitely. This periodic interrupts are called clock ticks. So most systems are going to have a backup battery that prevents the clock from losing the current time. And the current time is kept track of with benchmarks. The number of clock ticks increment from the benchmark moments. So for Unix, you have January 1st, 1970. And for Windows, you have same day and month in 1980. And then that number is then converted to real time. So who can tell me the three components of the clock?
The crystal oscillator, the counter, and the holding registry.
Great. You got it.
You gotta
Talk about
give,
the software side of
you gotta
clocks.
give them the candy.
So all the hardware does is generate interrupts at known intervals. Everything else involving time must be done by the software. The exact duties of the clock driver vary among operating systems, but usually include most of the following. So they're going to maintain the time of day, prevent processes from running longer than they're allowed to. They're going to account for CPU usage. They're going to handle the alarm system call. They're going to provide watchdog timers for parts of the system itself, and they do profiling, monitoring, and statistics gathering. So the first clock function, maintaining time of day, also called the real time, is not difficult. It just requires incrementing a counter at each clock tick. As mentioned before, the only thing to watch out for is the number of bits in the time of day counter. So with a clock rate of 60 hertz, a 32-bit counter will overflow in just over 2 years. So clearly that's not usable. So there's three ways to fix that problem. The first one is to use a 64-bit counter instead of a 32-bit counter. The second one is to maintain the time of day in seconds rather than ticks. And the third way is to count in ticks. So the second clock function is preventing processes from running too long. Whenever a process is started, the scheduler initializes a counter to the value of that process's quantum in clock ticks. At every clock interrupt, the clock driver decrements the quantum counter by 1. So when it gets to 0, the clock driver calls the scheduler to set up another process. The third clock function is doing CPU accounting. The most accurate way to do it is to start a second timer distinct from the main system timer whenever a process is started up. When that process is stopped, the timer can be read out to tell how long the process is running. Parts of the operating system also need to set timers. These are called watchdog timers and are frequently used, especially in embedded devices, to detect problems such as hangs. The last thing in our list is profiling. So some operating systems provide a mechanism by which a user program can have the system build up a histogram of its program counter so it can see where it's spending most of its time. So generally, there are two ways to manage I/O. There's interrupts and polling. Interrupts have low latency, so that is they happen immediately after the event itself with little or no delay. On the other hand, with modern CPUs, interrupts have a substantial overhead due to the need for context switching and their influence on the pipeline, TLB, and cache. And soft timers avoid interrupts. Instead, whenever the kernel is running for some other reason, just before it returns to user mode, it checks the real-time clock to see if the soft timer has expired. If it has expired, the scheduler event is performed, with no need to switch into kernel mode since the system is already there. So this is the second since January. So that's the second since 1970, I think.
Yeah.
First 1970. So that's basically what the Unix clock is counting up to. That's where it's counted up to so far. This is our little video. It's basically they're going to celebrate when it gets to 1, 2, 3, 4, 5, 6, 7, 8, 9, 0.